Welcome to Haltech Training Part 10. In this video, we're going to be checking out the acceleration enrichment feature found in our ECU Manager software. We're going to have a lot to learn, so let's get started. Let's get this video started by talking about our acceleration enrichment feature we're going to find in our ECU Manager software. Now, Haltech is going to be calling their acceleration enrichment this Transient Throttle Enhance. So it's going to be the same thing as what we learned in EFI Basics and EFI Advanced when we talked about the acceleration enrichment feature. It's just going to be called something differently. So the terminology is going to differ a bit from other standalone systems like AEM or maybe Motec. It's going to be called something different, but it's going to work the same way. So the principle is going to be the same. Now, Haltech implements their throttle enhancement a little bit differently than other ECU manufacturers. They're going to be using a asynchronous and a synchronous injector pulse during this throttle enhancement or acceleration enrichment. And we're going to learn all about that in this video, and we're going to learn how to set our transient throttle up and the little tips and tricks that I use when I do my tuning. So without further wait, let's jump into the video so you can see how this is all going to work. All right, so let's go ahead and open up our file here under base maps, our test file. Let's open up that Sport 2000 file. So in this video, we're going to be talking about our transient throttle. Now, the transient throttle is just going to be our acceleration enrichment. Now, Haltech just prefers to call it transient throttle, so it's going to just be the difference of terminology. And you're going to find this when we go between different kinds of standalones. We're going to call the same concept two different names. So it's simple as transient throttle, acceleration enrichment. We went over that in EFI Basics and EFI Advanced, so the concept that at this point should be somewhat familiar. So to work with the Haltech transient throttle, it's going to be implementing in a little bit different way than most other standalones. And we're going to be going into all of that. So if you open up your file here under ECU Navigator and you don't see your transient throttle, that's going to be because if we go into setup, main setup here, it's not going to be populated. We haven't selected it. If we go into our advanced, under functions, we're going to see that in this particular case, our transient throttle enhance has been checked. And that's why it's set here. So if I uncheck it, it's going to disappear from the window. If I check it, it's going to appear. So when I do my main VE table tuning, I like to turn off my transient throttle enhance. So if I just go ahead, turn this off, click apply, go to OK, and I go into my main fuel table and I'm doing either my open or my closed loop process that we just learned about in a previous video. Regardless of whatever I'm doing, I want to make sure that the values that I'm populating in this VE table to get my air mass model correct are going to be accurate. I don't want to go ahead and have skewed data. So when I'm watching my wideband and I'm going through the table, I want to move in very smooth, gradual throttle increments. I want to make sure that I'm not stabbing the throttle and really jumping in the table, because I know if I go and change my throttle a bunch, it's going to change the amount of airflow that comes in suddenly. It's going to create a lean condition, and therefore it's going to make me try to fatten up this table and to compensate for that. So before you go in and we do any transient throttle enhancement tuning, we want to go and make sure that our main fuel table here is going to be tuned as accurate as possible. Now, you're going to run into this situation again. If you blip the throttle, it's going to have a lean stumble. What we're interested in to build this table up is having gradual throttle movements so that we can go through and characterize the amount of actual air mass coming in the engine under normal throttle movement compared to having that large change or that delta throttle change as we hit the throttle and try to increase our load or our RPM very quickly. So let's go back into here. Let's turn that transient throttle enhance back on, and let's go jump in and take a look at everything we're going to find in here. If we click apply and OK, we're going to go up now into our Excel tuning page that we've created, and we're going to jump into our settings here. Now, this is going to be some of the most basic things that we have to program and set up to define our number of ASIC pulses and our transient throttle trim and a bunch of other data we're going to find here. Now, the first thing we're going to find is this number of ASIC pulses. This is going to be a little bit different concept than what we're used to thinking about. We've talked about the acceleration enrichment, and we kind of understand that we have a single injector pulse that happens when we command either from our VE table, that's calculating the air mass to the fuel mass to injector pulse width, and it's pulsing the injector to deliver the amount of air fuel that we're telling it in our target air fuel to achieve. So we have that idea all worked out. But what we haven't really talked about, and the concept is going to be a little odd probably at this point, is going to be we're able to actually inject more injection pulses in a single engine cycle to deliver more fuel instead of just increasing that injector pulse width when we trigger a throttle enhancement request or the acceleration enrichment. So what this represents is an asynchronous pulse. Now Haltech is going to call any pulse that's delivered normally through the injector a synchronous pulse. Anything that's going to be additional pulses in an engine cycle is going to be called asynchronous pulses. So just think of it as the ability to add more injector pulse widths or smaller injector pulse width during an engine cycle. Now, at very low engine RPM levels, we know that the engine cycle time takes longer because the engine's spinning slower, so we have more time to inject the fuel. So we're going to be able to use these async pulses very effectively at low engine speeds compared to high engine speeds with the engine spinning very fast, and the amount of time to spray the injector really starts to decrease, especially as we get up to 7,000, 8,000, 9,000 RPM. So we're not going to be using their async pulses at very high RPM levels. But we need to define how many pulses we're going to allow to occur during an engine cycle. So in this case, we have a value of 4. So there's going to be 4 async pulses allowed per engine cycle. And the typical values are going to be anywhere from 3 to 5. I've never needed to go either lower than that or higher than that, just for kind of a frame of reference here. The next thing we're going to find is our async delay time. Now this is going to be in place so that we don't constantly have async pulses occurring when we're tripping our transient throttle. So you can think maybe a drift car, an autocross car, where you're pedaling the throttle on and off very, very quickly. If we didn't have this delay time, we simply just set it to 0, it would constantly be adding a bunch of async pulses as we're pumping the throttle. Now, we have to keep in mind, when you're pumping the throttle very rapidly like that, there is going to be airflow change, but the airflow is going to have to slow down and speed up, and if we're pumping the throttle rapidly, it's not going to have this massive change in our air mass as we'd find if we were off the throttle, slammed it, and got on the throttle. That would have a huge change. If we're constantly pumping the throttle, there's going to be a constant air mass moving into the engine at different speeds, and it's not going to need a drastic async pulse to achieve our transient throttle. So this delay time is going to count for those rapid pulses. This is in seconds. Anywhere between 1/2 to 1 second is going to be normal for this async delay time. And this value right here has been populated at 0.8 in the base file here for the transient throttle setup from Haltech. Next, we're going to find our delta deadband, and this is going to be accounting for the actual amount of throttle change before the transient throttle feature will be kicked on. So we use this to, if we have a throttle position sensor that may be a little bit noisy, if we have the sensor as we're driving around just constantly shows that maybe the throttle's varying a few percentage of throttle, and that is going to allow this transient throttle to constantly kick on. And what we're going to find is we're going to have, if we look at our async injector time and our sync injector time here, so we're going to see that they're constantly kicking on, that the transient throttle here active will go from off to on and off to on, and we just really be wasting fuel. We notice that our wideband would probably be rich or fluctuating in air fuel. It's going to constantly be adding these additional injector pulse width as we're driving around, and we don't want to have any of that. We want to make sure that we can dampen some of that out. Now obviously if we go under setup, main setup here, if we jump into our inputs and our TPS sensor, we want to make sure this filter level is reasonable so that we filter out any kind of voltage fluctuations that the sensor might have. So if you notice that you do get some fluctuations, if you're steady throttle and you notice that's fluctuating a little bit, go ahead and increase your filter level from 5 to 8 or 10, and then go back in and try it. You don't want to go and create any more work for yourself in this transient throttle, increasing this delta deadband any higher than you have to. If we increase it higher and higher, we're going to find that we're going to have the lag time when the actual transient throttle kicks on. We want to be able to catch any kind of actual throttle movement or delta throttle movement that's going to be significant. So we want to set it as low as possible, but we don't want it constantly kicking in, and that's not going to be ideal. So we use this delta deadband here to account for any kind of rapid changes or small rapid changes in our throttle movement, so we don't kick a async or the transient throttle enhancement on. Next, we're going to find our transient throttle trim, and this is going to be an overall multiplier against these other tables here. Now, I typically don't use my transient throttle trim. This is going to be something that if you don't want to go ahead and deal with tuning any of this other tables and you want to do so quick and dirty transient throttle trim enhancement, when we look here at our async and our sync time, we're going to see that we have injector pulse widths are going to be associated with that when we plot it out on a live when we're tuning. this will just add a percentage multiplier to those calculated injector pulse widths. So for example, if we see that our sync time here is 2 milliseconds, our async time is a half millisecond, if we type in a value of 50, it's going to increase both of those injector pulse widths by 50%. It's going to be, again, an overall multiplier. So it's going to happen everywhere when this transient throttle would turn on. Again, I leave the 0, but you can use that if you feel the need to do so. Next, we're going to find our enrichment. So the transient throttle load source is going to be a table based on engine RPM here, and then our actual delta throttle. So if we jump in to the setup here, to table setup, if we look, the axis is actually set on transient throttle load. And we can see that parameter is going to be associated here, TT deload, or transient throttle delta load. So in order to set this table up right, we have to have the maximum value here is going to be the highest value that we can register here on this deload percentage. So what I normally do to make sure this table is going to be correct for my application, I turn the key on, the engine off, and I start hitting the throttle very quickly. And I watch this TTD load percentage here, and I see the maximum amount that I was able to achieve on this channel here. If I was able to achieve 70, for example, I would have to go ahead and repopulate this last breakpoint here in my table to 70. So I go up to setup, table setup, and I set this to 70. Now you also can go in and change the amount of breakpoints here. Now there's 4 available. We can't add any more. That's fixed. But we could change some of the scaling on the rest of these if we found that we wanted to maybe have something between 10 and 70 that was better representing our delta throttle here. We could go in and select these two and use the interpolation function. We can see if we click apply, it's going to apply those changes here. Okay, and then that would reestablish a more correct delta throttle to our table here. So this table is going to be based on the concept of at lower engine RPM, at smaller throttle changes, we're going to have more airflow rushing in the engine and more need for the transient throttle with acceleration enrichment to kick in so that we're not going to have that lean stumble. And as we go up in engine RPM, we're going to see that the values in the table decrease. And if we go up in our change in throttle, we're also going to see that it decreases, because at larger changes of throttle here, we're going to find that we don't need as much injector pulse width that's going to be added because there's going to have much less air mass coming in our engine. So we're going to see the effect where it increases from here in the corner, kind of goes up and decreases, and the same thing as we go up in our delta load is going to decrease as well. So the values in the table are injector milliseconds, so going to be pulse width based. And if, for example, if we notice if we're hitting the throttle and we've tuned our base VE table very well, we know that's good. If we're hitting the throttle off of idle and we notice that it's starting to run lean, then we can go in here and we can actually add it maybe like 50%, and then we can go ahead and watch what our wideband's reading, and we also can watch this async and sync time, and we can see how much more they're delivering and see if it feels better and it's delivering proper air fuel. So it's going to be one little trick to go ahead and set up our transient throttle load source, and we want to only have as much in here as we need. We don't want to crank these values up if we don't need to, because that's going to just add a ton of fuel here. We want to make sure that we add a reasonable amount of additional injector pulse width based on how much this transient throttle is actually requiring and what our air fuel is reading and how the throttle feels, so make sure it feels responsive, but we don't want to see it's constantly pumping a bunch of fuel. We watch our wideband as we're activating this, and we're watching our TT active. We're going to make sure that we're not just dumping excessive fuel for no reason. Okay, so for the next table we're going to find here is a percentage asynchronous delivery. So this is going to define how much of our transient throttle, when it's turned on here, when it goes active, is going to be delivered async versus synchronously. So if a value of 0 in here, it's going to be percentage. 0 is going to signify that all of this transient throttle enhancement is going to be delivered synchronously. Now, we just talked about that when we looked in our settings here. We're able to have most of our transient throttle delivered asynchronously at lower engine RPM here, because we're going to have more available time to pulse the injector. So there's going to be more time for a couple extra injector pulses to occur during an engine cycle. And as we get up in engine RPM, there's going to be less of a need and less time available to have any kind of transient throttle taking place. So we're going to deliver everything synchronously. So I typically set this table up starting at 1,000 RPM here. 100 is the highest we can go. I typically go about 100% here at 1,000 RPM, and then I'll transition it out to 0 at 4,000. If I just select the whole table, click L, it's going to linear interpolate. So I'm going to be able to watch the status in my async versus sync time here as I'm delivering my fuel. So we're going to be able to easily account for what's going on and be able to tweak these values here. So this is going to be a good way to make sure that at higher engine RPM here, there's going to be just synchronous pulses because, again, we don't have the time available as our cycle time shrinks to be able to deliver any more additional ejector pulses. Likewise, we can really make sure that we do everything synchronously down here at 1000 RPM. Now, one thing I should note here is if you have higher than 9.5 milliseconds required or output from the asynchronous channel here, for watching as this becomes active and we're tripping it, anything higher than 9.5 is going to deliver any additional fuel automatically into the synchronous injector time. So if we're going into this enrichment table and we're cranking the values up because for some reason off idle has a lean stumble and we need a ton of fuel, if we some reason have 10 or 12 milliseconds here, we're going to be watching this. It's async will cap here at 9.5, and then the synchronous will absorb the rest, and you'll see the rest of the difference in that. Next, we're going to see our percentage enhancement here, another enrichment. Now, one thing that you have to make sure is whatever your enrichment table here is in your load source, we can see here it's at 70. We have to make sure that this percentage enrichment is going to have the last breakpoint here be 70. We have to make sure that it's set up this way. Otherwise, we're going to run into problems. So we're going to go into setup, table setup, and for my example, I just said the highest delta load that I could find would be 70%. Then I'd go in and characterize this maybe a little bit better here. I'd select the whole table and click apply. And then what we're going to find is that's going to represent the percentage enrichment at the highest load would be 100, and at the lowest, it typically is going to be 50. Again, I'd go through the table here, I'd click L, and I'd linearize these, and that's going to be a multiplying effect based on how much the delta load that we have, the percentage. So again, make sure whatever you find in this TTD load as the highest value here, you go and populate the last breakpoint in this table to that value, as well as this enrichment. They have to match, or there's going to be problems calculating the transient throttle correctly. So it's just something I want you guys to keep in mind. So next, we're going to find our coolant temp enrichment. Now, this table is going to be helping us account for the wall wetting effect that we're going to get on a cold engine. So you can see the values in the table here at 32 degrees. That's 300. That's 300% multiplier. So if we were looking at our synchronous and asynchronous events being triggered here, and we were calculating 2 milliseconds, let's just say, on our async, and we're calculating 1.5 on our sync, and we multiply it by 300%, we'd see these values would increase by 300%. And when we see we go up here to full operating temperature, it zeroes out. I always suggest that you have this zeroed out when you get up here. We're not going to have any additional need to add some coolant temperature correction enhancement. 300 is the highest value you can add in this temperature correction. 300 is probably sufficient. 2 to 300 is sufficient on these very cold temperatures. And then we want to go ahead and just transition it out as we get up to our operating temperature. So whatever that's going to be, when we jump into setup here, we can actually edit the coolant temperature. So if you have an engine that runs relatively cold, maybe 160 is its normal warm-up temp, don't be afraid to go repopulate this with 160 and then just do a horizontal interpolation here. So if we just to quickly do this, 160, we grab the table, use this linearize feature, apply OK. It's going to repopulate that. So we're going to go ahead, we'd set this to 0. We go ahead and use the L function. That's going to linearly interpolate. And then we'd have our table populated. So don't be afraid to repopulate this table if you need to do so. Now the last thing we're going to find here is our enrichment decay rate table. And this is going to be how quickly the asynchronous and synchronous pulses are taken out. So looking at the values here, they're going to be in milliseconds. And it's going to be how much milliseconds per engine cycle is removed to get back to the normal values here that are calculating from our base table. So when we see this TT active go from on to off, we're going to be turning off the transient throttle. And then these values here are going to represent how quickly we want to take this async and sync pulse out. We don't want to continue to pump fuel. So the higher the value here, the quicker it's going to pull out this async and sync time once our TT active goes from on to off status. So we've turned it off. So we can see here on the colder temperatures, we keep it on, we have the fuel stay in a little bit longer, and that's because of that wall wetting effect. And as we get up to our normal operating temperature, we're having a higher value. So you're going to have a trend like this. These values are probably sufficient to start with. If you notice that as you're hitting the throttle and this goes off, that the air fuel stays a bit rich when you should just go out and run back to the table, you might go ahead and increase this to maybe like something like 0.8. We'd go ahead and double the decay rate and see what that effect would have. So it's going to be trial and error setting up this decay rate table. But the idea of the asynchronous and the synchronous pulses should make a lot more sense now, and why we want to go ahead and deliver our fuel for our transient throttle or acceleration enrichment asynchronously, so that we don't have to go ahead and disrupt our synchronous pulse that's going to be calculated from our main VE table. And again, if you want to go ahead and just simply increase that rate, we're going to go into our table here, and we can just multiply in percentage and increase these values to increase our async and sync injector time. And hopefully we're going to be able to get our transient throttle the way we'd like. We're going to see that our air fuel is relatively stable. Now, I want to point out, when you're doing your acceleration enrichment or transient throttle tuning, remember that your wideband sometimes is going to sample slower than these events will happen. So when we're doing our live logging, we're doing our live training, and I run through an example here and I plot these out, you're going to see these move incredibly fast because we're talking milliseconds here. So it's incredibly quick. You're going to see they trigger and come in and out, and your wideband sometimes won't show you that reaction to that in milliseconds. It's going to happen so quick that we may or may not be able to capture it accurately. So I like to tune my transient throttle based on feel. I want to make sure that my engine can rev crisp, it's smooth, I don't have any kind of hesitation feeling, and ultimately my wideband has a decent air fuel. So when I hit the transient throttle, I do expect this to richen up. Maybe if I'm running at 14.7, it might richen up to 13.5, 13.0 air fuel. I shouldn't see it dip into the 10s and come back. It means it's just way too rich. And if you have a stumble or hesitation going on and it goes that rich, you might actually have a rich stumble because the values are too high or this is kicking in too much. So you have some things to explore and change with the acceleration enrichment tuning, but make sure you keep it off when you're doing your main VE tuning, then turn it back on after that table's been tuned so you can see what's actually required and what's needed for a transient throttle. I find that I don't need as much as my transient throttle as I thought I might have to multiply and add these and increase these values. If I have a very well-tuned base VE table, it's going to require less transient throttle to be populated in these tables here. Okay, so that wraps up Haltech Training Part 10. In the next video, we're going to be taking a look at our boost control feature in our ECU Manager software. We're going to have a lot to learn, so I will see you in the next video.